Hi everyone, welcome back. In this video, I will work an example of a percent yield type problem. It's really important that in general chemistry you begin developing problem solving skills. So I took an example from one of my previous exams on calculating percent yields, but in order to do so, you need to figure out your limiting reactant and then how much of the excess reactant is left over. So let's go ahead and get started. A student synthesizes aspirin in the lab by reacting salicylic acid with acetic anhydride in the following reaction below. So you see here we have salicylic acid with its molecular formula, acetic anhydride to produce aspirin, and acetic acid. The main product we're most interested in here is the aspirin. All right. So the first part of this question is asking us if a student reacts 1.5 grams of acetic anhydride with 1.5 grams of salicylic acid, what is the maximum amount of aspirin the student could obtain in grams? When we're asking for the maximum amount of aspirin, we're asking for the theoretical yield. Now, in order to do so, we need to figure out if salicylic acid is the limiting reactant or if acetic anhydride is the limiting reactant. And the limiting reactant produces the least amount of product. So in order for you to determine which one is your limiting reactant, you need to set up two separate calculations to figure out how much aspirin each reactant could produce. All right, so I'm going to abbreviate salicylic acid as SA and acetic anhydride as AA and aspirin as ASA because the name for aspirin is technically acetyl salicylic acid, so ASA. And I'm going to start off with 1.50 grams of salicylic acid. I'm going to use dimensional analysis to make sure all the units cancel out and don't make any mistakes. You need to use the molar mass of salicylic acid to convert from grams to moles. And you can calculate the molar mass from the molecular formula given above. And so in this case here, grams of salicylic acid cancel out, and now we're in moles of salicylic acid. But remember, we're trying to figure out how much of the aspirin is theoretically produced. And so you always need to do a mole-to-mole ratio. Now, in this specific chemical reaction, everything is 1:1. And so moles of salicylic acid cancel out. And now I'm in moles of aspirin. You never want to skip that step because not all chemical reactions are 1:1. So you want to make sure you always remember to do the mole-to-mole ratio. And then finally, we want to figure out how many grams of the aspirin could be produced. And so we need to use the molar mass of the acetyl salicylic acid, or the aspirin. And then moles of acetyl salicylic acid cancel out. You get 1.95652 grams. And make sure you're always labeling what chemical you're referring to. In this case, we're referring to the aspirin. I've abbreviated it as ASA. And how many significant figures would you need if you had to give the final answer here? Correct. You would want to use 3 sig figs because the measurements are in 3 sig figs. And when you do dimensional analysis, everything is in multiplication or division. And so the answer you would report would be 1.96 grams of ASA. I'm going to keep this answer here as well because we may use it a little bit later, and so it's important to not round mid-calculation. All right, so let's do the same setup, but for acetic anhydride. So we start off with 1.50 grams of acetic anhydride. Remember, we want to convert to moles, so we need to use the molar mass of acetic anhydride, which is 102.09 grams. And we don't want to be in acetic anhydride, we want to be in aspirin or acetylsalicylic acid, so we need to use the mole to mole ratio. Whenever you want to convert from one species to another in a chemical reaction, always use the mole to mole ratio. All right, now we're in moles of acetylsalicylic acid. And now we want to convert to grams. And so we're comparing apples to apples. Grams of acetylsalicylic acid or aspirin. When we calculate this, we get 2.647 grams of the aspirin product here. And now we're comparing that 1.95652 grams to the 2.647 grams. And once again, we would report that final answer if we had to report it to 3 sig fig. So let's just do that real quick. And now we need to determine which one is our limiting reactant. Is our limiting reactant the salicylic acid from this calculation here, or is it the acetic anhydride from the second calculation below? And that's where you need to always fall back on that definition of what it means to be a limiting reactant. Remember, the limiting reactant produces the least amount of product. And that's why we calculated the product, and we chose the aspirin product, not the acetic acid product, because we're more curious about aspirin in this example here. And so based on that definition, it turns out that salicylic acid is our limiting reactant, right? Because it produced the least amount of product as shown here. It produces only 1.96 grams versus the 2.65 grams from the acetic anhydride. And the reason why it's the limiting reactant is because once we run out of that, we cannot produce any more aspirin. We have no more salicylic acid left to do so. So the salicylic acid, once again, is the limiting reactant, which means that the acetic anhydride is the excess reactant. And as a scientist, it's really important, as a synthetic chemist, to identify what the excess reactant is and how much of it's left over. Because in the end, you need to purify it from your product, the aspirin. And so technically, if you're running this experiment in the laboratory, you would quench the acetic anhydride with some added acid to convert it all to acetic acid. Acetic acid is a liquid, and aspirin is not super soluble in water, and so you could filter out the aspirin from any acetic acid or acetic anhydride that may be left over. And so it's important that we understand that, so we find a way to purify our product from any unreactant reactants or byproducts, in this case acetic anhydride and acetic acid. All right, now in order for us to calculate the mass in grams of the excess reactant left over, we always need to start our calculation again from the limiting reactant. So we will start with 1.50 grams of salicylic acid, convert that to moles using the molar mass. And now we want to convert to moles of acetic anhydride because we want to figure out how much acetic anhydride needs to react with our salicylic acid. And so 1 mole of acetic anhydride for every 1 mole of salicylic acid. And then we need to convert that to grams. And moles of acetic anhydride and salicylic acid, that all cancels out. And now we're in grams of acetic anhydride. And so this is how much acetic anhydride has reacted. So in order for us to find out how much is left over, we need to take what we put into our reaction flask. This is initial amount, and subtract out what was reacted. To figure out what is in excess, what is left over. Now remember, this is subtraction, and when we do subtraction, we report our final answer to the fewest decimal places. And so in this case here, you would report your answer as 0.39 grams of acetic anhydride in excess. All right. And just kind of a side note here, dimensional analysis is a really useful tool to make sure that you have the setup done properly. When I was doing research, I wanted to make sure that whatever reagents or reactants I was measuring out, I was doing it appropriately. I never wanted a calculator error to mess up my reaction. You know, that can be costly in terms of safety. It can be costly just in terms of money. You don't want to waste materials. And so even though it may seem like a little bit more work, and you know, I find that sometimes students want to take as many shortcuts as possible, at least with dimensional analysis, you can be confident knowing that your setup is correct. And so I highly advise that you do this, and this is why I'm recording this video, to give you an example of how to approach these types of stoichiometry problems. All right, so let's answer the last question. It says the student isolated 0.330 grams of aspirin after drying in a vacuum oven overnight. So we're confident there's no water left over. It's just pure dry material here. What is the percent yield for the reaction? So percent yield, let's just remind ourselves, is what over what? Actual yield over theoretical yield times 100%. And usually when we're referring to percent yield, we're referring to one of the products. And so in this particular word problem here, it says that the student isolated 0.330 grams. That is the student's actual yield. What was the theoretical yield? The theoretical yield was the maximum yield produced from the limiting reactant. So in this case, that 1.95652 grams. Right, so let's go ahead and plug that into this equation here. We have 0.330 grams, and then we're going to plug in the theoretical yield, and this is the aspirin. The theoretical yield from the limiting reactant. And when you plug that into your calculator, you should get 16.8666% yield. And how many significant figures will we round that to? Good, to 3 significant figures. So in this case here, the student obtained a 16.9% yield for this particular synthesis here. All right, so I hope that this was a good example for you on how to approach percent yield problems, a good reminder of what it means to have a limiting reactant and how to calculate that, in addition to calculating what excess reactant and how much is left over. Thank you for watching, and see you next time.